art, which is like the bytecode or art bytecode. So this makes it runnable on Android. And then we have to compile Android resources, and then eventually we end up with like zeros and ones. So it runs on an Android system. And all of that is actually pretty complicated, but I'm going to try and like simplify it a little bit more. So I think a good way to do this is like visualize a project you've worked on. If you worked on like a multi-modular project, that will help. I like to think of these modules on these boxes on the screen as your like modules of code. So this is where you have like your user code, your like database code is all separated out separately. And at the very bottom, this might be your app module. Now, if you're imagining your multi-modular code base, like imagine the connections between your modules. So this is where you're importing other modules, importing code, things that make your app actually do things. And just imagine them connected with an arrow pointing between each box, which is referencing other dependencies or other modules. And you'll find this is taking the shape of something. It's taking the shape of a graph. The most feared data structure, I think, in programming. Specifically, it's a DAG, directed acyclic graph. Some snazzy words there, but basically this just means it's you got a bunch of boxes that point into each other. That's the directed part. And the acyclic part means there's no loop in it. So basically it means there's no infinite loop and you can build your code. And this is kind of important to what a build system does. This is like part one. It knows about your code. It knows all the relationships between your code. And it's all done through a DAG. Next, I want to talk to you about what actually happens when you click the play button. I think it's got a better name than play, but I call it the play button in Android Studio after you've made some changes. So let's imagine this. This is our DAG. It's back. And in the top corner, we got this orange box. Treat this orange box, well, sorry, I like to imagine like the build with different colors. And orange here I'm treating is like, here I've changed some code. And this is in the top right-hand corner. And these yellow boxes are code which is forced to change because you've changed code in the orange box. So this is forming what we call an incremental build. So this means you're not building your entire graph, you're only building a little bit of it. And this is what we spend most of our time doing as we're at work every day. You're making a little change, clicking the play button, and then part of your project is rebuilding. I think part of the puzzle of what we do is trying to reduce this to like as few boxes as possible that need to be recompiled. If I were to catastrophize this and make it as dramatic as possible, you could say if incremental builds take up an hour of every developer's time in a business, and you multiply that by the number of developers and you multiply it by the number of days in the year, you could say you're really burning a bunch of people's, you're burning your employer's time. Oh, sorry, burning your employer's money, but your developer's time. And that's really what those boxes represent, is like compilation time. And that's what we're trying to avoid. And that's hopefully what we'll try to be able to do by the end of this. Yeah, I've forgotten why this slide is here. I can't see my speaker notes, so let's go to the next one. Oh, I remember why this is here now. Okay, sorry. Yeah, so it's quite important actually. It's like, why does this square turn orange? And there's a whole bunch of reasons. You can change files, you can change a build file, you could delete it, you could upgrade libraries, change the version of Kotlin, loads of things. But I think the most important thing is is when your ABI changes, your application binary interface. And for something that's so like important to build systems, I think it's not really like referenced so much, and it's kind of like hidden away in your build system. So we're going to try and like understand what this is now. And I'm sort of summarizing it as like a list of every public thing inside of a module. And it's really as simple as that, is how other modules see your code. Another way to think of it is it's sort of the thing that influences the drop down when you're typing code and you have an autocorrect. Is where all of those things sort of come from. That's how I imagine it. So let's look through some fake code I've written for this presentation and see how this influences the ABI itself. So It's a very standard code, I guess. If you write a lot of Android stuff, at the very top, we have a reviews repository. It's just an interface that has one function on it called get reviews, and it returns a flow of reviews. Underneath that, we have a private implementation of this repository. We don't care about the code inside of it. We're only interested in like the top level stuff. Underneath that, we have another function, just a factory function I've written that allows people to access this private class. So this is all well and good. This is our Kotlin, but what does this actually look like as an ABI? And again, it's hard to really put an ABI on screens. This is like my mental model is how I think of it. It's really just a list of things available to you. So you have your public review repository, you have your public function again. You can see there's a flow on there and the type of review, and then the function. And that's really what your ABI is. And now we should look at a few things that can impact your ABI as you're working, as you're writing code, like tapping away on the keyboard and like pressing the play button. And I think we're gonna go back to basics here. Like visibility modifiers have such a key part in a key place in your build. We're gonna go through public, internal, and private. I'm gonna assume you're all fairly familiar, but we'll do a quick summary. So public, this is always available to us. We don't even have to write this modifier, but it's very important. And I actually think it's the worst modifier. And the reason for that is the impact it has on your ABI. So I've added this other function called product validator at the bottom. We don't care what it does. We just care that it's public. And let's have a look at what this does to your ABI. It adds a new function to it called product validator. And it seems like a small change, doesn't seem that dramatic, but it's what leads to this happening to your DAG. You're forcing the compilation of 4 other modules and the 5th one, which you've changed. Again, this is sort of like a mental model. There's many other things that can influence this, but this is the general like approach I have in my head. So we could assume that adding something to your public ABI is like not ideal. But what happens if we add something that's private? Private basically means you can't see anything outside of scope. So this is just top level. This means it's not going to be seen beyond your module. You could put a private function inside of a class, and it can't be seen beyond the class. So here our product validator is private, and this is the change it has to your ABI, nothing, which is great news because in general this means only the module up here needs to recompile. This is like the ideal situation where not a lot of stuff needs to be recompiled. You're not burning your employer's time, not wasting your time, and this is what we're chasing. The other modifier is internal, and this basically means something's private inside of your compilation unit, but not outside of it. So it's very similar to private. So we got to put an internal keyword on our product validator, and this is a change to the ABI, nothing. And this is the change to your compilation times. Oh, sorry, this is the change to your DAG, nothing at all. Well, except for the module you've changed. Again, this is the ideal scenario. So the thing I just drill home is every time you put something public on your module, it has an implication on compilation times. It's not always bad, but it's just something to bear in mind. The next thing we're going to talk about, we've done our Kotlin. Now we're going to talk about Gradle. This is a talk about build systems, really, so we should probably talk about it. This is going to talk about I'm going to go through how you declare your dependencies. And there's many ways you can declare your dependencies, but the most common are API and implementation. Now, this is going to be a real demonstration of the English language, as I don't mix up API and ABI over the next few slides, hopefully. Okay, so here's our ABI. So we're just going to review what we have, like our rough ABI for this module. We have our review repository, we have get reviews. But the key thing that we haven't really touched on is this flow. This isn't a class we've defined. It comes from a third-party dependency. comes from the Kotlin Coroutines library. All you need to know is it comes from somewhere else that's not our code. And then we have our repository factory underneath, and that's all well and good. So how do we get our flow? We could get it with an implementation. This is a way of defining a dependency, and the Gradle docs are quite good. It sort of says implementation. An implementation is consumed by, sorry, an implementation dependency is consumed by your module. So basically it means the dependencies are available in your class path, and you can make use of this dependency. And let's say we've done this, we've added the Coroutines library, and you now have the code we've just gone over. What happens if a third party uses your another module uses your dependency? It won't compile. Oh no, that's not good. But why does it not compile? It's because we are only consuming a dependency, we're not going to produce it. So the flow class, which we've spoken about, is not available for others in the repository, sorry, in their module. So how can we fix that? We can use an API dependency. This is a dependency which we will consume and produce from our module. Consume means we can use it, but produce means other modules who are using your code will also get this dependency. There's many other nuances to this, but I think this is the best way to think about it. So now when we change our dependency to this, so it's an API dependency, not implementation, our code will compile. Yay, that's good. Yeah, I should have tried live coding this just to demonstrate it, but you just have to trust me that this works. So next up, really the final thing is I've started calling this the visibility modifier dependency dance. I don't think that's going to do it justice, but what I want to try and leave you with is if you want your modules to be reusable, you want to try and reduce compilation time, or even you're creating a third-party a library that other people are going to use. Your visibility modifiers are very important to changing your ABI, but the classes on your ABI that you're making public or private or allowing others to consume are driven by your dependency declarations. And as you put dependencies on your class path, that might mean you have to change your visibility modifiers so your builds will work correctly. I think I need to practice that a little bit more, but there's something in there, remember. And that's everything. Thank you. And if anyone has questions, no, this way. No questions live, but if you have questions, I'll try and pretend to answer them.
I don't know if anybody in the Zoom can hear us, but I'm guessing they can hear you. I do have a question, but if anybody has a question, you can feel free to go. Okay, I can throw my question.
So what is the practical example? When would you use API instead of implementation?
I guess a good example to be super concrete is if you're using, say, maybe a tricky example, if you're using Dagger, for example, to do dependency injection in your code, most modules may have a dependency which has inject on it, or you have to bear with me through this. I think I picked a difficult example. It has the inject annotation on it, and that is technically going to be made public if you have a public constructor. And because of that, you should really put your Dagger dependency, or more accurately Java X inject, on your API dependency. Otherwise, you'll have issues with compilation down the line. I think that was actually not the best example. So if you want me to try another one, or we can chat after, let me know.
I have a question. So I'm thinking, thank you for the presentation. That was pretty good, but I'm wondering, so let's say I have this module that's a shared library that I made internally beginning, because everything I wanted to use is in that module, but then later on, I want to use that component in a different, let's say, plugin, and I want to call it down the pipeline. But now, all of a sudden, it complains, I need to make it public. And then I think based on that, I think it creates the overhead, that extra time. So I'm wondering, what would you recommend in that situation?
I suppose if I've understood, you're saying you have a reusable thing that's like used by a lot of different places, and changing that will have an impact on like compilation time. I guess in that situation, it's not necessarily a bad thing if it is used in a lot of different places. I suppose something I should have summarized a little bit more is maybe if you have code which is used in a bunch of different places, but or isn't used in a bunch of different places, but is public, you could have a bit of an impact on compilation time. So I think in your scenario there, it's like absolutely fine.
So I've thought about that.
Yeah.
Mentioned about the private and public IoT. Basically, by simply looking through your code and trying to remove any unnecessary public values that you can really drastically reduce your build time.
Not necessarily. Like I suppose potentially. You basically reduce your public surface area, and that might mean if you're changing something that's private and not used elsewhere in the code base, you're just not going to trigger as much compilation kind of. Sorry, it's very hand wavy on stuff.
Can I come back to that question? Sorry, I didn't quite understand the example.
Yeah, no, sorry, that was a terrible.
I think I read that like the library, if you write the library, that's when you would use it.
Yeah.
I never did. So like, is there a case where you must do it? Because when you try to give this example, you said it might give you compile problems, but like might is different from will.
I think I got a much better example, which I probably should lead with next time I do this presentation. I don't know if we've all used retrofit, for example. It has a dependency on, say, OK HTTP.
Yeah.
That has to be essentially an API. I don't think it's exactly the same. Otherwise, if they don't provide OK HTTP to you via retrofit, you can't compile the code when you try and use when you try and pass in an OK HTTP into your retrofit. So that's an example of like a third-party library that needs to like satisfy the API to make sure it works when you add it to your project. Yeah.
You said that you can like export like library via API keyword, right?
Yes.
What happens if the user already has that library but a different version? Do they conflict?
Oh, that could be a whole other talk. Yeah, it could potentially conflict. Yeah, it could. It comes down to like Gradle and how it does dependency resolution, and like it's a little bit tricky, and maybe it's a little bit outside of my wheelhouse right now. But essentially, yes, it is a risk. But it's just something to be aware of. I'm not even going to try and explain it now. Sorry to be. Yeah.
Cool. Thank you so much.
Thank you.
And we're sorry again for the technical difficulties. I think Amanda is next. I'll have to.
Do you want the? There you go.
They're gonna go in.
Yeah, go good.
Hello, Amanda, can you hear us?
Yes. Yeah, I can hear you.
Okay, you're up next. Jordan just completed her talk. Did anybody have any questions online for Jordan? We're good. Oh, no, I see Navid is here too. Navid? Navid, do you want to say hi? Hello?
Yes.
Oh, sorry, I just joined. I don't have much context yet, so I literally just joined the first talk just end.
Yes, I'm gonna remove my blur. Wait. Amanda, I'm just gonna show you the room so that everybody can say hi. Hopefully it doesn't ruin it. Wait, what happened? Well, can you see
no,
everybody
that's
here?
Yes, I
Say
can see
hello,
everyone.
Amanda. There we go. Is that great?
Oh, it's helpful.
Okay.
All right. I'm gonna get my screen set up and we'll get going.
Oh, yeah.
Okie dokie. Let's see.
Everybody can hear my voice. Okay, perfect.
Okay, great. And if you like, feel free to keep your camera on in case people have questions or anything.
Let me see. No, but you can't see the other, yeah. So you know what we're gonna do is just I wanted to pin your presentation. Can you do full screen? I don't know how you do that.
I am screen sharing now. Can you see my screen?
Yes, we can see it, but I want to see how we can show it with oh,
Yeah.
that's better. Okay. I'm IT now. Okay.
Okay.
Oh, well, that's going there.
Yeah.
All right. I guess is that okay?
Yeah.
Okay, great.
You can go.
Okay, cool. Yeah, I don't know why I like mess with my bangs right before, but hi everyone. It's so nice to be at the meetup virtually. My name is Amanda Hinchman Dominguez, and this is Kotlin Coroutine Mechanisms, a surprisingly deep rabbit hole. Sometimes you think you know coroutines, and then after a while you're like, do I really know coroutines? Like, do I know them at all? And this is a really common phenomena. You know what I'm talking about. I feel like this is a pretty accurate depiction of the average developer journey exploring Kotlin coroutines. They're really easy to start using, and it doesn't require mastery to be productive. But then you spend time with them, and eventually you start wondering why your coroutines are doing that. Then you're forced to understand coroutines, like really understand them. So this talk is aimed to kind of get you to that point. Quick show of hands in the room, and I know I can't see you, but do people know what I'm talking about? Like, I've been working with them for a while now, and once in a while I have to like step back and be like, do I actually understand them? Do I know them at all?
I think you got some thumbs up. I'm
All
trying to see
right.
if there's a way we can put you up there too as you present. Just hold on.
Oh yeah, take your time.
Yeah, I'm trying to see. Anybody know how we can do that? I'm not a Zoom savvy person. Yeah. If we can pin her.
Yeah, just be to put that hub screen. It's not just show
Okay.
what was it? How did it happen before?
Yeah, I did that.
Yeah, and then we get this and just share. Yeah, she's
Okay, perfect.
yeah, and what this corner is
Yeah.
okay.
Oh,
Like this?
yeah.
Okay, awesome.
Put that to
All
first.
right.
Oh, so that she can see us, right? Oh, you would.
Yes.
Oh, well, this is already meant. Yeah.
I think just let you the computer.
Okay.
So you can keep it,
I think IT sent me a long message apologizing. I'm like, oh no, you guys are fine.
All right.
Oh, there we go. Look at that.
Cool. I think I see people, so that's a start. I see one person at a time. Oh yeah, I can see you all. That's nice. I'm gonna try to pin that. Can I pin that for me? Or will it do it for everyone? Okay, cool. Thank you so much. It's always nice to kind of get a little interaction in. But yeah, no, we'll get back to the journey of the average developer exploring coroutines. So the point of this talk is to get you from this why did it do that to have this very deep understanding that allows you to be able to kind of get out of those situations. So show of hands, would you say, would people feel like they're a little bit closer to like Kermit the Frog?
Yes.
Yeah. True. And hey, that's all right. That's what we're here for. So, okay. Yeah, I've heard a lot of feedback about Kotlin coroutine use, like one being that, oh yeah, Kotlin coroutines, it's not perfect, it has its warts. And I do agree with that in some regards. So for example, some of the existing tooling for it has some room for development. Definitely the testing aspects, I think it's gotten better, definitely. And then there are a few API edges as well, but I will hold your hands virtually when I say this. Most of these pain points that developers experience tend to come from a mismatch between expectations and coroutine design. You see, coroutines were designed to lend towards structured concurrency. And so if you follow the rules of structured concurrency, it will actually solve the majority of all your coroutine related problems. So hot take, not that hot of a take though. In this session, we'll cover what coroutines are and why it's there, and how coroutines naturally lends itself to that structured concurrency paradigm. Okay, because we have a short talk, I wanted to share further works that I've written if you want to keep reading into Kotlin coroutines. So I have a list here. Some of them are free, some of them are not. And I sent the links to Madonna, so she'll be sure to share these after the meetup. Yep. Okay, what do coroutines solve? Coroutines is not just a new concurrency framework. It solves a lot of the problems we had previously with existing Java threads. Coroutines help us manage concurrency, cancel operations safely, and avoid the pitfalls of threading nightmares, especially in terms of both concurrency and cancellation. Okay, let's talk about the first problem that coroutines tries to solve. And the first problem is that threads are expensive. They're expensive to spin up, they're expensive to cancel, and they're pretty expensive to context switch. Android in particular has a limit on how many threads can run concurrently, and all systems have a memory limit. So you're already working with the idea that you have a limitation on how many threads you can use. And the OS controls the thread scheduling, not the developer. So this makes it really hard to control the life cycle of a thread. So just because you ask it to stop doesn't mean it will. It'll do it when it wants to. Okay, next, kind of like to add on to this problem, threads are blocking in execution. So each thread can only run one task at a time. And if you wanted to have multiple bits of work running, you need to have multiple threads. And then that kind of goes back to that expensive, like threads are pretty expensive. So you have a limits. Oh. And we have, when those blocking tasks, so like, I guess the way I would describe the life cycle of a thread is you start a thread, it does some work, and I said it'll finish whenever it wants, but in reality, it will finish when the work is done and the system is able to look up, hey, is it time to close it? So there's kind of like all these conditions around it. So if you're not able to complete the work for any reason at all, then the thread cannot finish. And those blocking tasks in the thread, it can choke a program. So there are long-running operations without cancellation. There's also resource starvation. And also, let's see, I put in this image of the art runtime heap. This is actually kind of an interesting thing. So Android in particular, we know it's a bit stingy, especially in terms of resources. Every application has its own processing heap. And the art heap, like the Android runtime heap, organizes objects by age, size. There's this like younger generation, older generation, permanent generation. And then they also have thread local allocations. So what you're looking at are thread local allocations. And these thread local allocations are grouped by regions, which are otherwise known as threads. And the important thing to know is that no one region can access another object within another region. So it kind of exists on its own timeline, and you can't access the objects from the other threads. So it's another aspect of inflexibility with the expensiveness. Okay, coroutines are cheaper for the sole reason that you can run multiple coroutines within a single thread. Like you can just have multiple asynchronously running, kind of overlapping. And the other crazy part is that when you're using coroutines, they manage all this for you. This is something you don't have to worry about, but it's also possible to start work on a thread and it could actually resume work on another thread. So it can jump around a little bit. But these are details you don't have to worry about. The most important thing to take away is that we should favor coroutines because we can do a lot more with a lot less resources. Okay. All right, problem number 2, threads are hard to manage. Threads are not immediately responsive to this cancellation request. So when a source thread calls for a cancellation of a target thread, it will send a cancellation signal. And that cancellation signal is actually more of a request. So it's just like, hey, could you stop the thread? But the catch is the target thread has to notice that the cancellation request is there in the first place in order to act on it. So like I said, just because you ask a thread to stop doesn't mean it will do it when you ask it to. So yes, have people worked with threading issues before in their jobs? I know it's like one of the worst issues I continue to deal with today. Yeah, but at least it keeps us in a job, right? So okay, problem number 3, thread cooperation is prone to side effects. So multiple threads accessing a shared mutable state can produce side effects that are difficult to control. So we previously talked about how, especially in Android runtime, we have these thread local allocations, these regions where we can't access anything within each other, but if we had some kind of shared resource that both were accessing, you're gonna get side effects. All the woes of concurrent systems that are risky kind of come from this concept of having a shared mutable state that multiple things are accessing. So side effects are the root cause of race conditions, deadlocks, hard to produce bugs. And for those that don't know, side effects are changes to the overall state. Okay, so here is a good example of what this could look like. So we have some code with a transaction history. There's a little bank service as an executor thread pool. And then we have 3 bank users, Bailey, Stevie Nips, and Bailey. And in the bank user runnable, when we start running the task, we take a transaction history, which is currently a hash map. So it's not thread safe. There's no form of synchronization. And we try to change the values. And then if you look down to the runtime part, you'll see this Bailey deposited $40. And then there's a history check with that. It's very interesting that Stevie Nips is already at 100. And then Bailey deposited 200. So you can see that even though we put everything in a certain order, it is running out of order. It looks like Stevie Nips somehow already had the transaction history, yet it printed last. There's a lot of stuff going on here. So there's a couple important lessons from this. Thread execution order is not guaranteed. Just because you put it in a certain order doesn't mean it's going to come out or print that way. And then the other part is that what you're seeing here is an example of race conditions because it has this element of inconsistency from what you would expect. So threads, super difficult to work with. Thankfully, coroutines, well, you should know that coroutines can produce side effects depending on the kind of setup that you have. So it's possible to end up with the same problems, which is why you sometimes hear people say, oh, well, you know, coroutines has its problems too. But in reality, it just depends on the way that you set them up. So the same is true. Multiple coroutines accessing the same shared thread resource can also result in unintended side effects. And what you're looking at here is a visual example of just some basic nested coroutines getting launched. And this is kind of how you would, what you would consider maybe like not designed with structured concurrency in mind. Because, and the reason for that is because, well, we'll get into that later, but you'll see that a lot of things are overlapping. We're starting and stopping things without regard to waiting to whether it finishes or not. So these are sort of like the characteristics or how it might look to not to end up with a system that could produce side effects. Okay, so let's talk about structured concurrency and how it can contain those side effects. So structured concurrency naturally helps contain those side effects because we are reducing the ability to have multiple things access a shared state at the same time. So it's about having a little bit of order with what we do. Hold on, I gotta plug in my computer so it doesn't die. Okay. Okay. So what is the structured concurrency paradigm? Let's talk about it. So I've done a lot of studying for like the last few years. And what I can say is I can boil down structured concurrency to these two basic rules. One, a parent coroutine always waits for its children to complete. And then two, a child coroutine never gets lost. This actually lines up with Kotlin coroutine features. And if you set them up in a certain way, you can use coroutine scopes, jobs, and contexts to fulfill the first role, which is making sure that a parent that launches a child, like the parent always waits for the child to finish before continuing. And then this bit about making sure that a child coroutine never gets lost. And coroutine exceptions and cancellation mechanisms actually offers a lot more options to ensure that this is an automated mechanism and more. So I hope we have time to get through that. But we'll start with structured concurrency. So the first rule of structured concurrency, which is a coroutine always waits on child completion. So a structured concurrent system waits for all tasks to finish before leaving the scope, and no task is left incomplete or abandoned. So this will guarantee that your app behaves predictably and gracefully. Okay, when a child coroutine fails, by default, it will fail silently. But this is not a nice experience, and it can be a bit ugly to work with. So there is something you can do for that. I do want to brush on some of the other aspects here, which is not only will it fail silently, but if there were any children that it had running, then all of those children will get canceled. So like that can be a good thing, right? Because it's nice to not have hanging threads, but you won't have record of it by default. And on top of that, unless you set it up a certain way, that cancellation does not get propagated back up. So it's really, really important to understand this, because people say, oh, like, why are things getting lost? Like, I don't understand. It's because this is how the default behavior works. And then, yeah, so structured concurrency addresses these problems of lost, failures, and exceptions in child coroutines. And the Kotlin Coroutines API offers a few cancellation mechanisms to ensure that a child coroutine does return completion, even if it fails. Okay, yeah, we already talked about that part. And so, yeah, I mean, ultimately, structured concurrency comes with mindful use of coroutine scope and context. They're used together to tie life cycles in a job hierarchy. And so it's super important to have intentional use of your scopes and contexts. But, you know, it's so weird when we start talking about this whole scope and context thing. I think this is where things start getting a little crazy. I love lifting the hood to check on the internals of these things. So here's my question to you. And raise your hands, depending on what you think it is coroutine scope and coroutine context the same thing? Is it difference? Okay. And if you don't know, that's okay too. Yeah, it's a hard question. So the answer to this is, I'm gonna say it's kind of 1 and 2. Implementation wise, they're actually the same thing technically. As you can see here, there's this public interface, which only has one thing, and that is the coroutine context. You're like, what the heck? Why is there just a wrapper like this? But like legit, it looks like this. So why does it exist like this? Well, the scope and the context comes down to the intention of use. All right, so this is the implementation details for the coroutine context itself. So coroutine context is implemented in the form of a composite pattern to be able to create unique and traceable tree structures. This is similar kind of to how the internal of Jetpack Compose views work. So let's see, we go to, was there anything else I wanted to add to this? I wanted to point out, let me make sure I didn't skip over anything, because in this code, we have the get, the fold, the plus, minus key. Then we have this interface with the gets, the fold. So yeah, the get, the folds, the fold in particular, that's what creates this composite tree. So this is a pattern that is definitely worth looking up. I do have a photo somewhere a little bit down here, but ultimately, after looking at the code, we can summarize and say that even though implementation-wise are technically the same, we can look at coroutine scope as the container for the context. So it defines the group of coroutine jobs working together. So it's just what groups it all together. And then the coroutine context describes is a set of elements that describes the coroutine behavior. So that might include information like the dispatcher, the job, and optionally coroutine name and other information. Okay, and then this is a really great interpretation of how it looks. This is a re-rendered image from Roman Elizarab's series on coroutines. He's written a few of these. Really great article, highly recommend reading it. But as you can see, there is a parent scope there, and then there's a child scope. So there is some launched child coroutine, but then you see all this bit with like the scope context and the parent context, and it gets kind of crazy. You kind of see this folding that's going on, but the parent job gets combined with some input for context, and that creates that parent job. And when you launch a new coroutine, you tie that parent context to the child job that you want, and it creates this child job. So that's kind of how it looks. And the reason why we are talking about this is because there is a concept of job hierarchy versus scope hierarchy. They're actually two different things. So if we look at this picture, the hierarchy between parent scope and child scope is a scope hierarchy. And then the hierarchy between child job and parent job is its own separate hierarchy. Okay, so job hierarchy. When a job is launched in another job, they create a child-parent hierarchy. Every coroutine has a clear parent-child relationship within a scope. And this is important because the parent coroutine is going to be aware of the child coroutines that it has, and it has relative control over that. Okay, but when it comes to a hierarchy with scope, it's a little bit different. We can't view it as the same thing. So when there's actually different kinds of coroutine scopes, but in particular, if you launch a brand new coroutine scope, this would not by default inherit the parent scope. So if you do that, that basically breaks structured concurrency. You want to make sure that you're inheriting from the same scope if you want to have that structured concurrency. Okay, so a new scope breaks structured concurrency. I know what I'm gonna say before the slide even shows up. And yeah, so we have this code right here. We have the run blocking. We have a launch. So the run blocking will be the parents. The job launch will be a child of the run blocking. And then we have within that a child for job called task one, which is an async task. I'd like folks to take a like, I don't know, 20 seconds to take a guess as to what they think the order of the printing will be. Oh shoot, you know what? I did you all dirty. I thought I was gonna have an outcome for this. This actually might be later. We're definitely I really psyched you out. Sorry. That may have been there are a few like that. If we have questions at the end, I can pull those up. Those are so fun to do. Yeah, I thought I was gonna have an outcome for that. I apologize. So we're looking at this new scope. Where is the new scope? There is no new scope actually. So what you can see in here is that everything in here currently is technically structured, and there's a few reasons for that. There's the fact that everything is inheriting from the same scope. And then the other important part is that you'll see that every parent is waiting on the completion of every single coroutine that's being launched. So for example, a launch is normally a fire and forget. So if we had not remembered to include that job.join, this would have not been structured. But we've made sure that every single parent, and then of course there's the async task, which is a deferred type. You have the await here. So that is forcing the program to slow down and stop and wait until everything completes before it moves on. So this is what it looks like. I don't see that new scope, but this is currently structured concurrency. Oh, okay, maybe we are doing something with that. Let's see. So I think the best way to actually look into how all this works, there's a couple ways actually. So the best way is honestly with logging. That is the most accurate way you can do it. Debugging gets a little bit weird. And there's actually, if you can work with coroutines on IntelliJ, you have an excellent debugger, but the same is not true for Android Studio. For the time being, I found a problematic way of doing it. And I think there is a GitHub issue or whatever the Android open source repository lives, I forget now, but we did open up an issue. So I'm really hoping that the Android team looks into it so Android can also have a nice debugger. But for the time being, yeah, this is This is the way you do it with IntelliJ, and then this is how you do it with Android Studio. You can only really produce it in testing. You can like use their API to do it. So it's kind of neat because so this one is done with, this is that nice GUI that I was telling you that IntelliJ has, but Android Studio doesn't have. And exploring this idea of coroutine scope and context, you'll see in the screenshot that there's this, oh, it's the same code. You know what, maybe we'll find what that output is after all, but you'll see in the debugging that we have the coroutine one, which is that blocking coroutine. Then you have the next one, which is the async job. And then that one's currently running. And then you'll see that in coroutine 2, coroutine 4 gets launched. Oh, this isn't even the same code, but it's very, very similar. And you can see that at line 25, that is where everything has stopped. And this is a snapshot that is captured at this time. And there's this little part here that you'll see where there's kind of like this nested loop hierarchy. This is all part of the same scope. That is what that means. And let's see, there's this deferred coroutine. I don't know if I'm forgetting anything else from here, but highly recommends taking some time to explore kind of what this looks like. And then if something exists in a different scope, normally it won't share that hierarchy at all. It'll probably just show up on the first level. So what is this? Let's see. This is another screenshot. Oh, yes. Oh, yeah. Another thing I wanted to point out as well, you can see in the debugging that there's current states with each of them too. So this is kind of interesting because right now the code in the screenshot, the code is, the debugging point is stopped at the creating task. And at that point, the first coroutine is technically suspended, and that makes sense because we're currently in the first child job. It says the other ones are running, so you can actually see, oh yeah, you can even see here coroutine 1, and then there's this job in bold. The fact that these two are not under the same hierarchy kind of shows that there is a break in the scope. So if there is a tree that you see, that's that scope that I'm talking about. Okay. All right, going back to all this. Are we gonna put, yes, we are. Okay, we, there it is, there it is. So this is how you would break structured concurrency. Simply by using this coroutine scope. This is a new instantiation of it. We're no longer inheriting from the scope that is provided by the job. Okay. You should know that not all scopes are created equal. So this one, there actually is an next part. I will give you like 10 seconds to go through and take a guess whether each one respects structured concurrency or not. Yes, is this something that folks have thought about before? Or is this something, like for me, I'm not gonna lie, I ignored all this for a long time. I'm like, who cares? It's just different. No, it means different things. Violent. This is like coming for your hey, this is a really hard topic. This is like a crazy hard topic. All right, we're gonna see what the answers are. Okay, yeah, so there's quite a bit. There are only 3 cases, especially if you're an Android developer, where using a scope does respect structured concurrency. So like I said, a brand new one, a brand new coroutine scope will break it. So don't do that. Unless you're very deliberate. Why? Like the only case I can think of that this would be okay would probably be like if you're in a service class, you can't use the view model scope or not a life cycle scope either. So that would be an appropriate case for using, because You just have to remember that if you launch a new scope, you have to manage the life cycle of that separately, because it's not going to manage the life cycle automatically. It's just its own different life cycle. So that's why you want to make sure that you're going to use the lowercase coroutine scope if you have to do that, because that does inherit the parent scope. And then there's a viewModel scope.launch and the lifecycle scope.launch. Those two are from Android X. I'm sure a lot of you are familiar with the viewModel scope.launch. And then there are more use cases for lifecycle scope.launch, especially around like compose and stuff. So these are the general rules for it. Coroutine scope, use it judiciously, but I would say generally for an Android developer, if we're working with structured concurrency, for the most part, we should have like one root scope and generally not worry about it after that. There is a specific reason why you might want to use a coroutine scope. If you can use it as a way to like contain the blast radius if something happens, so that's like one way to use it. All right, let's talk about also coroutine extension functions. So this can also respect structured concurrency as well, because you're inheriting the scope that you're using. So this is also acceptable. Can people see in here my screen? Oh, I know, like that thing was moving for a while. Oh, this is, when I say this stuff is hard, it really is. I had to like do a lot of digging. This is found deep in the forums, or in the Kotlin Coroutine issues. And I do think Roman Elizarov summarizes the rule of thumb around coroutine context and scope really well. If it's using a coroutine context, when you're doing like some kind of launch or you're starting a new coroutine, and you have to put that coroutine context in there. So if you're using a coroutine context, don't add a job if you want to keep structured concurrency. And then if you are using a coroutine scope when you're launching, then that should have a job. So kind of weird to think about, but I think this is a good way to boil it down. And of course, there's links for that. I think I'll send a link to these slides for Madonna too, so people can dig into this stuff a little bit more. And then how are we doing on time? Because my timer says I'm over time.
I think, what time is it now?
6:40.
6:40. Okay, I think we have 20 more minutes.
Okay, I'll get through this as fast as I can, and I'm really sorry because this is the most important part too, so apologies. All right, let's talk about automated cancellation mechanisms. This is that second part to structured concurrency, which is making sure no child gets left behind. Actually, though, for real. So Kotlin coroutines have certain mechanisms that you can set up, and you should set up, that allows you to have automated cancellation mechanisms to ensure there's not going to be dangling work, and that there's a way to recover it pretty easily. So you have a few APIs to start with. A lot of you might be familiar with these, the cancel and join with timeout, which is it cancels and throws an exception for a timeout cancellation if too much time has passed. And then there's also with timeout or null. If you use any of these, you're going to need to wrap these in a try catch to be able to catch exceptions around this sort of thing, which is fine. There's also the use of try finally. I know this seems kind of obvious, but there is like a little bit of a fun twist with this. So you have your try catches, but did you know that you can use that finally to clean up certain mechanisms? So this is something you shouldn't run into too often, but it's good to know that if something gets canceled or we finish a work and you need to clean up the resources, you can still do that with the finally, especially with coroutines. So, and if you need to cancel something and for some reason it needs to be a suspendable of any kind, you can use with context non-cancelable to do that. This is kind of in a rare instance, but it's good to keep in mind if you have resources you want to clean up, like Bluetooth use or something. You want to shut that stuff off. Okay, let's talk about default cancellation behaviors for unhandled exceptions. We've talked about what happens if a coroutine fails or cancels. We know that it's going to try to cancel its child coroutines, and it may not always tell the parent that, oh, I failed out. So canceling a job propagates a cancellation downward to all child jobs. And then if you were to cancel, if a scope were to be canceled, then the scope is canceled and so are all the child jobs. So this is where it gets crazy, because if you end up with an unhandled exception, by default, it'll cancel the job that the exception occurred in, and then it will actually travel all the way up to the scope if it is not handled. So it can be a little bit inconvenient. I think this is what people complain about a lot. So the thing is, you can isolate that failure by creating that subscope. So remember how we talked about how there's a way to create kind of like this, like the lowercase coroutine canceled. So you can actually wrap it around like that if you want to contain the blast radius. There is another way that you can do it too via supervisor scope. This is actually the main way. You want to use supervisor job and supervisor scope. There's some nuances and differences between supervisor job and supervisor scope, but if you see this coroutine scope supervisor job, that does create a supervisor scope. So in this case, we isolate that task 1 failure, and to create a smaller scope that captures a parent scope, all you would have to do is wrap task 1 and task 2 in a supervisor scope. Okay, we can isolate it even further by adding that little supervisor scope that I was talking about. It's like coroutine scope, but supervisor scope, because it actually notifies the parent scope that something did happen. Okay, what kind of coroutine exceptions are there? There are 2, exposed exceptions and then unhandled exceptions. So exposed are things that can be caught with a try catch. And then you have unhandled exceptions, which can make your application crash or leave it in a weird state, and can leave side effects if there are silent failures and we just keep running stuff. Yeah, it can get a little weird. Okay, so there is a way to automatically handle your unhandled exceptions, and everybody should be doing this at the root scope, which is creating your own custom creating your own custom exception handler and then registering it to the scope. So this will stop that exception propagation where just things travel all the way up and just trashes the whole thing, and you can avoid a program crash that way. So I would look at registering a CEH, like kind of like your last chance to handle that unhandled exception. And yeah, so the coroutine exception handler is conceptually very similar to a thread uncop exception handler, but intended for coroutines. Oh, one other nice thing too is that registering a custom handler will also be printed to the stack trace, because without that, you're not going to know where. I can't tell you how many times like in the payments industry, we're like, we don't even know what's wrong because nothing ever got registered. Please do this so you know what you don't want to spend your incident time trying to find something that's not there. So we want to always create a trail, and that's what this does. Okay, a couple things about this formula to registering a coroutine exception handler. So you have your custom coroutine exception handler, and you'll see that we do the scope.launch, and you'll also see that I added this supervisor scope in there. Where did that CEH go? Oh, there it is. It's in task 2. It's right there. So the nice thing about this is you don't have to have like a try catch at every single level, because if you did just try catch all the time, you're going to have to do it at every level. and it actually allows the exception to propagate up. There's going to be no leaks, like no hanging threads, no nothing like that. And so, yeah, there's like basically 3 steps to doing it. You want to make sure that your launch is a coroutine root builder of some sort. So it's the launch or the async. And then there has to be a scope that it's assigned to, and then a supervisor scope. Okay, this work is still from a lot more. I wrote 6 months, but it's actually more. It took me 6 months to write this. There is one of these. I don't know if there's much else. I think that's everything for me. I didn't leave a thank you, but I do have, I'm gonna go back to the slide that has all the extra materials, but that's everything for me. Thank you. I hope you enjoyed my talk, and let me know what questions you might have. Thank you.
Wow. I know this is always a very complex topic, but the floor is open for questions.
Questions in chat.
Okay, so we have, okay, you have a question. You can go on first. We have a question here. I'll check the chat too. Go on.
What is an example when you want a non-cancelable coroutine?
What is an example of a non-cancelable coroutine?
What is a non-cancelable?
What'd you say? Sorry, the last part?
When would you want to use like a non-cancelable? Because you like mentioned that.
Oh, okay, got you. Yeah, there's only one case for that. Because you pretty much, you'll never use this. There's a lot more slides than I thought. Yeah, you'll never, oh my gosh. Yeah, I'll say that for the most part, you'll almost never run into this. Like I said, this is a very, very, very specific use case where you want to, and this is also if you don't have a coroutine custom exception handler too, because like that would be kind of the equivalent. But let's say you do have a try finally or try catch finally. You would want to use with context non-cancelable. So this is only, oh gosh, usable when technically when you're at that finally, you're outside of the coroutine scope. So only in this finally is the only time you'll ever use this. And like I said, you shouldn't have to run into this a lot, but like I said, this is for something like you want to stop a Bluetooth connection from running anymore. Like that would be something where, let's say something happens and now we're shutting the whole thing down, but you still need to access a suspendable function to clean it up. So this would be that one case.
Cool.
And any other questions?
I see some questions in the chat too. I think.
Oh, shit.
Yeah.
I totally missed that. Let me see. Oh, okay. The 2 questions are, how would you compare the try catch finally with run catching and coroutines? Oh, and I'll start with that one. I would compare that as I'm gonna say, I mean, they're kind of different, but what I would say is the run catching itself is the try. The run catching itself is the try. And if you wanted to have, you know, caught except like catch or the finally, that would be, you need to have run catching, then at the end on error on success. It's super important that you have the on error on success. I see too many times that people use run catching and they don't realize that they actually ended up swallowing their exception because they did not include the on error. And then the next question, is that a sufficient enough answer? Oh, yes, it is. And then the next question is, should there be different approaches for IO versus CPU intensive coroutines? Yes, yeah. So in terms of dispatchers, we actually just had a conversation about this at work. Yes, it is important which dispatcher you use. You should always be using IO for IO related things. So that's accessing the database. It's network calls. And the thing about it is that with IO dispatcher, you're using a minimum of, I think, like 64. Let's see, you have access to like just like 64 sections that you're using. And then for CPU intensive coroutines or operations, then you would use a dispatcher. And then if you need to switch between the two, I would use with context. So like, let's say you have a bunch of computational stuff and then you have a network call or a database call at the ends. I would use with context to switch to that. The point is that you want to use what is most appropriate because a dispatcher will have as many sections as many threads to access for coroutines as I think like the maximum number of CPU cores for whatever is being used. So there's a difference between 8 versus 64. And so you just want to use what is most appropriate. Like for example, you wouldn't want to put all your database stuff under the default dispatcher because that would be the CPU computations. And if you end up running out of room, then you're not giving room for other expensive CPU computations to be able to run. So it's important to be a bit judicious about which one you're using when. Okay, I think I have time for one more question.
Hello, I have a question.
Hello.
I have a I'm actually a little bit confused about one of the slides that are about like parent and child scope. It was like it was a diagram. I wonder if you can find that.
Let's see if I can find some of those example ones too while we're at it. But is it this one?
No, it's like it's about like when
I know what you're talking about. This one. Is it this one?
Yes, that one. Sorry. Yeah, about that one. I guess yeah, I'm still learning a bit about coroutines, but like adding scope context and additional context creates parent context with a parent job. I guess like inside the scope, so I see that child job like inherits parent's job too, but I don't understand why there's a child job inside child context. I guess maybe I'm a little bit confused about the plus sign there. Do you mind explaining that one more time?
Yeah, no, I can see maybe this wasn't, trying to draw a graph like this is so hard. But yeah, basically you're right, the child job it's like basically connected to the parent job, like it inherits the parent job naturally. But the parent context also holds the parent job. So that is also true. And when a new child coroutine is launched, what actually gets combined is the parent context and the new child job, which technically would be connected to the parent job. It's that folding in thing. And then when we combine the parent context with the parent job, then you create this new child context, which holds that child job. So that child job inside the child context is the same as the child job on the outside, but basically like this is like, that's that new thing that we fed in, and together we fold it to create a new context, which still holds a reference to the parent job. I hope that makes a little bit more sense. It's not the best
A
way
little
to
bit,
visually
yeah.
show.
I didn't know if like
Yeah.
those two things like exist at the same time, or
No. Yeah, you know, like probably this could have been displayed as like two images, really, like a 1-2 situation. So the parent like imagine the parent context with the parent's job and the child job. Like those are the two things that come together
yeah.
at that plus sign, and then like that's specifically what gets combined when a new context is being created. It's so weird to think about.
Okay. Yeah, I'll definitely look into it a little bit more, but I can sort of see. Yeah, I was just, yeah, I guess the
Yeah.
formula thing about like the child job plus parent context equals child context with a new child job.
Yeah, no, it gets pretty confusing. And you know, actually this is one reason why I recommend really like giving this thing a try on IntelliJ Studio. I don't know like if this shows exactly what I want, but you see how it's like these are all the jobs, right?
Yeah.
Oh,
Yeah.
I didn't like, is there another photo that shows more? Okay, like you can't really see the Bailey, settle. Thank you. Good, settle. Sorry, I have a dog. And you can see that there is this concept of a job hierarchy. Right. And yeah, so this is actually why I recommend getting this debugger out, because I think if you I don't know if you're going to be able to see the combination of the context getting combined together, but there is actually, I think, another thing that you can do specifically with this. You can add some logging to check on the context at each level. That is something I would recommend.
Yeah, that sounds like a good idea.
Yeah, because it gets so weird to think about. And then also, I don't know if I'm gonna find it off the top of my head, but Roman Elizarov had this like really awesome, like short little text diagram somewhere in his keeps. And I don't know if I ever bookmarked it, but I'm gonna find out if I did, because it's about coroutines. And it's also, I don't think I'm gonna find it because I'm just gonna see if I can coroutine issues maybe. Oh, I did save it. Okay, check this out. Because this is how I find out all this stuff. And there's also a really good channel. I'm not really on it much, but these people know exactly what they're talking about. Just be careful though, because some people are like, well, can I technically do this? And I'm like, yes, you can technically do that, but I wouldn't. But yeah, this, if you're on the Kotlin Lang Slack, there is a Coroutines channel, and they get into really quite crazy questions like that sometimes. But yeah, so I think this is a good way to look at. Another way to look at how scopes and coroutines kind of get mashed together when we're creating a new coroutine. So there's another aspect of the composite structure that I did not touch on. I just like didn't even mention it. So the question here is like, what the heck, what's going on with this plus operator? Like, remember how we kind of had that boiled down, like, if you're going to do this, do this. If you're going to do that, do that. Because you're like, well, like, so this plus sign right here is that composite part that allows us to combine the elements together. And I think it does go back to, let's go back to that image right here. I think that is what that plus is supposed to signify. Kind of this part right here, like kind of just like mashing this all together, and then that's what that's supposed to be. So the effect of that is with the composite tree structure. It's called a composite because when you use this plus sign, it creates like a mapping of like, what did it say? A map of context elements. So it's very, very similar. Like I thought this was like, I don't know why this stuck with me so much, but it's much like a regular mapping. So like this is kind of, it's conceptually the same idea, but we're getting a little bit into like burrito thing. So don't think
Yeah.
about it too hard, or you'll end up thinking about the burrito. So
No, this is really helpful. I really appreciate it. Yeah, I'll look into that thread more.
Yeah.
But yeah, I get that better.
Yeah, no, definitely. It's like you have to think about it hard and then take a step back, because and then think about it hard again. This particular issue that I started is issue 143, if folks wanted to look into that. But yeah, it's tough because like, yeah, there's a lot of stuff on it. There's a lot by him. There's a lot of time kind of decoding, like, what does he mean? Like, but yeah, no, it's a tough topic. And I think the best thing you can do is to explore like ways you can break it and see what it does. And yeah, let me see if I have like one more example, because I did psych you guys out a little bit with a fake run, and I do have an actual run. This is actually from an older talk, which is named the same thing, which is why I think I confused myself and the rest of you. And yeah, I have a couple of these because it talks about like the difference between launch and then async. So it does have some of these. And I'm gonna just like jump to maybe the async one. Okay. Yeah, like we'll do one of these to see we'll give it like a 30-second thing. So this is the currents code. And then all right, so we have task 1, task 2, these are all launches. Remember how we talked about how launches are fire and forget? And then we have these 2 joins that we add, and then there's an additional task here. So when it gets printed out, there's like this like logging that I like to do too, and it makes this really nice. Like you can actually count and see which ones are being launched where. I'll provide a link to these slides too. This is from a totally different talk. It's like from a much more beginner talk, but let's see if I can get to that. So we'll see here that we have task 1 launch, then the delay hits, task 2 launches, the delay hits. So then it goes back to task 1 because we forced it to waits. And then everything is done. So then task 2 can finish. And then task 3 runs as normal. So if that is what all that does, then if we look at deferred, deferred won't print it out until you call awaits. So if we take that same code and then we change it to an async, why don't you take a few, like 20 seconds to guess what it will do?
We gotta grab the audience.
All right, so this would be the new output. We have task 1, launch delay, task 2, launch delay, and well, async, I guess. And then we have task 1 joins. Okay, so when task 1 joins, it completes. Then we have this task 2 status. Where is that coming from? Oh God, it's all the way down here. Okay. So this is where, yeah, we have task 2 happen, and then we have task 3 start finally. Okay, great. Then we have task 2. Oh, I think one's supposed to be the regular task. This may have been, I think this is supposed to be the regular task because that would make a lot more sense. Then we have the status. Then we have this complete. Oh, this is so interesting. So it actually completes early on. So no, this makes a lot of sense because it actually did complete earlier. That's the thing. It completed a while ago. It did do that. But we still had it wait to print at that point, and that's why it looks very similar. So this is this exercise right here is exactly the kind of exercise that I recommend. Like it's really, really like basic, easy stuff. But if you're trying to understand the internals, setting it up this way is kind of like making it a much simpler environment. You're like almost treating it like maybe like a pending queue, like a singular queue, and it's a lot easier to try and understand these mechanisms in this isolated environment. So this is what I recommend you doing, just like pulling out the IntelliJ Studio, putting in something super easy, and just seeing the difference between the logging, the debugger, and trying to understand what is the relationship to everything at that time. And it can reveal a lot.
Cool. Thank you so much, Amanda. I mean, I don't know.
Yeah.
I think this
I
was
hope
pretty
everyone
amazing.
enjoyed the talk.
No, I did enjoy it so much. I think I love the topic. I know it's a complex topic, but definitely requires a lot of concentration and time and a lot of learning too. And I have to say, I think my easiest way of learning Coroutines was because I was put into a lot of RX work back in the days and RX Java, RX Kotlin, building an SDK. So it was brutal. So when I see
Back in the
Coroutines, I'm
day,
like,
yeah.
oh, this is much easier for new developers. So yeah, but thank you so much.
Yeah.
And Jordan, thank you so much too. Again, I do apologize for the technical difficulties. We'll definitely continue to figure it out. And I would like for us to get a picture because you know what? We get funded with this for your company, so I'm gonna bring the photographer.
True. Send me the photo. Yep.
Wait, is she still here? Amanda?
And she went to get her.
I'm going to ask her.
I wasn't sure if I was actually in the photo or not.
Amanda?
Yes.
I have a question because I saw like on the list of resources you had like the code labs. So because I'm more of a beginner on learning about coroutines, is the code labs also a good way of like learning more about coroutines, especially with the topics for today?
No, yeah.
Yes, that code lab on Droidcon is a very extensive code lab. You could start from nothing, and then it's I think it's about 10 or 11 chapters long, and it's like a workbook kind of.
Okay, awesome. Thank you.
Yeah, and you can't buy it by itself. It's kind of like I think you just do the subscription, and then you have access to way more than just that.
Okay, awesome. Thank you.
But it's okay if you don't want to be in the photo, but it will be appreciated because I'm only gonna put it in our slide deck, you know, like, hey, you know.
Oh yeah,
So
just the links and stuff. Yeah.
And I'm gonna stand over here.
Okay, sounds good. Thank you.
No, stay there. Where are you going? You're a speaker.
Wait, what do you mean?
Take the photo with you in it.
Oh.
Cheese.
Social currency.
Awesome. Thanks.
What's up, Amanda?
Thank you. It was so nice to see you all. I really enjoyed that this still felt like almost like an in-person meetup. That's really nice.
Absolutely. Oh, it's my soft phone falling out.
Thank you so much.
Yes, thank you all so much for coming. I think,
Thank you.
yeah, thank you so much.
Mhm. Thank you again. I guess I'm gonna like click off, but it was so nice to chat with all of you.
Thank you.
Thank you.
Thanks. Bye.